Okay, hi, this is thermodynamics. Um, and it's a 50-minute class. I'm going to spend most of today going through the D2L site and the syllabus, talking about the class structure and that kind of thing. And then we'll get into we'll start talking about the class a little bit. Um, Everything in this class runs through D2L. Um, So to find D2L, go to the main Normandale webpage. So if you get to normandale.edu, um, go to the drop-down menu, current students, and D2L is one of the things there. And you log in with your star ID, and when you log in, it'll show you a list of the classes that you're taking. This is thermodynamics, so click on that. And the first thing you'll see is an announcements page. So each time I post something new or give you an assignment or whatever, if I want you to you know be aware of a test coming up or something, there'll be an announcement here. So this is really what you need to be checking regularly. Okay. Um, I would say check that every day. Um, and then all of the materials and stuff. So you'll be able to check your grades as we go. Assignments here is where you're going to put files when you submit them. But today we're going to be talking about stuff in content. So if you go down here to content, there are all these different options. I'm not sure what the different icons here mean. That's new, but I want to talk about the syllabus today. And there's some other stuff too. If you want to, um, if you want to, read ahead, watch ahead. There's some. I guess I would recommend, if you want to sort of read ahead at what we're going to cover, go down to these old lecture notes, and you can just sort of skim through these and sort of get a sense of what kind of topics we're discussing. If you want to watch old lecture videos, they're here. Once we get going, I'm going to be doing this like mostly a lecture class. Um, but instead of writing on the whiteboard, I'm going to be writing on the tablet screen up here. And so there'll be a video of everything I write. I would recommend, when I write something on here, write it in your notes. I think that's a good way to do it. But you'll always be able to go back and look at videos of what I've done later. Okay, so like if I go to, okay, what did I talk about? This is just some random semester. I don't know what semester this is, but that semester on September 23rd on the Monday, uh, this was what I talked about. And I guess I was talking about linear interpolation and um, the ideal gas law. And so you can just sort of skim through those and get a sense of what the topics are that we're going to cover. Okay, so today we're going to talk about, oh, and there's a list of equations here. So this is something that as you're working through problems that I assign, um, I would recommend just having this equation sheet printed out and just have it next to you. And I'll give you all these same equations on the exam. So if you get used to using it in the format here, you'll feel comfortable using the same format on the exams. But okay, we want to talk about the syllabus. So here is the syllabus. Um, it's a 3-credit class, and I'll talk about time expectation. So this is all just pretty standard stuff. I I think really like my engineering classes are probably on the easier side. I definitely think that's true compared to, you know, the average like university level engineering class, but it's a real engineering class, you know. And so you're going to have to do a significant amount of work. And if you're not ready to put in this amount of work, we should talk about it. You know, it's just not going to go very well, you know. Um, so here's just generally, if you go online and Google how much time outside of class should I put into a college class, you know, um, it'll say 2 to 3 hours outside of class for every 1 hour of class time. Okay, so let's think about the low end of that. So let's say 2 hours outside of class for every hour in class. Um, this is a 3 credit class, so there's going to be 3 hours of class time. That means that you should be putting in 6 hours at a minimum outside of class every week. So add those two up, and this is a, you know, at a minimum, this is a 9 hour commitment for a week. Okay. And if you have a week where you put in less than that, then you're going to have to count on making up for it at a different time. You know what I mean? Um, so I really think, I mean, I know that for the most part, people here are sort of early in your engineering classes. Not everybody, but so I would recommend that you go into your calendar and just find where in the week you're going to get those hours from, you know. And if it's going to be hard to get those hours into your schedule, then at a minimum we should talk about it. Okay. So yeah, feel free to come ask me questions about that, but expect, you know, 9 to 12 at the high end hours of um, hours of week hours of work per week put into this class. Um, my name is Guy Olakin. I have a master's degree in biomedical engineering and a PhD in engineering mechanics. Um, you can just call me Gaio. My office is on the physics hallway on the first floor, S1311. Um, Although that's not where I do my office hours. I do my office hours in the tutoring center uh, in C2190. Um, you can contact me by email or phone. But the best way to contact me is to use the D2L messenger. So let me show you where that is. Um, so if you're on D2L, anywhere inside D2L, once you've logged in, up at the top, there are these icons here. And this one is the messenger. And so if you go there, you can send me a message through that. And it's just a nice organized system. So I like that one. Okay, class time Monday, Wednesday, Friday at this time in this room. My office hours are Tuesdays and Thursdays from 1 to 3 in the tutoring center, and Fridays from 1 to 2 in the tutoring center. And everybody's schedules are different. If you have trouble getting to my office hours, let me know and we can schedule Zoom calls or meetings outside of those. If you can make those, um, I would highly recommend uh, getting in a habit of coming to the tutoring center during some of those times and just doing work in the tutoring center. Um, if you get in the habit of doing that every week, you know, you can work on stuff. Hopefully, there'll be other students in the class working on stuff that you can talk to. I'll be there to ask questions if you get stuck on anything. It's just a really nice setup. And in the past, when I've had students who've made a steady schedule of, you know, going to office hours and doing work, they've done much better than, you know, than the average in my classes. You know, I think it's a really worthwhile thing to try to do if you can fit it in. Um, there is the time for the final. It's the last day of finals week. Also, I'm sure a lot of you are taking this and statics at the same time. Um, the final, this is a long way away, so you don't really have to worry about it yet. But the final for this class is scheduled from 11 to 1 that day, and the final for statics is scheduled from 2 to 4 that day. Uh, it's not much fun to take two finals pretty much back to back like that. So if you're taking both classes, um, when we get a little closer to it, if you'd like to take one of those a different day, we can certainly schedule that. Okay. The prerequisites for this class are Chemistry 1061 and Calc 1. Um, and we will use quite a bit of calculus in this class. Um, although I'll try to give kind of refreshers of whatever calculus we need when we get to it. Would you mind? Oh, there we go. Um, recommended reference books. Really, for this class, you don't need any books. Everything that you need, I'll give you in lectures. Um, those are mostly in here so that if you have any issues with transferring these classes when you go to your university, it shouldn't happen in Minnesota, but sometimes like if you go to a different university out of state or something, they'll want to know more about the class before they transfer it. And these reference books give them a good sense of like what kind of stuff at what level we cover things. But if any of you are thinking of taking the fundamentals of engineering exam on the way to becoming professional engineers, uh, getting credentialed as a professional engineer, these are really good reference books for getting ready for the standardized tests that you need to take. This Moran and Shapiro book is a full textbook, so it's sort of expensive. The Shams Outline is a paperback book, so it's cheap. It's $25 or something like that. And it has a bunch of problems with full worked solutions. So I always recommend getting Shams Outlines for any technical class you take. It's a nice thing to have around. But while you're taking this class during this semester, I wouldn't mess with outside sources. I would just understand what I'm saying in class. If you have trouble understanding something, ask me questions, because really I'm just very specifically trying to get you ready to answer the kind of questions that I'm going to ask on tests. So other people might have other priorities, what they think is important to emphasize. I'm going to talk about my priorities and then I'm going to test my priorities. Um, the topics we're going to cover. So we're going to talk about um, sort of thermodynamics related laws of physics. Thermodynamics is largely about energy exchange. You have talked about energy exchange in Physics 1. Well, Physics 1 is not a prerequisite for this class, but many of you have taken Physics 1, I know. And when you talk about energy exchange in Physics 1, you're talking about mechanical energy. So you're talking about exchanging energy from potential energy to kinetic energy. And that normally, most often in Physics 1, you're talking about exchanges of gravitational potential energy with kinetic energy. So you have something with a lot of potential energy at the top of the hill, and then it rolls down the hill, gives up that potential energy as it descends, but it gains that energy, turns into kinetic energy. In thermodynamics, we're adding a new thing to that. And that's not, gravitational potential energy isn't the only kind of potential energy. You also talk about spring potential energy that works similarly. You can talk about potential energy due to electric fields and magnetic fields. But That's all mechanical energy. So there's no thermal energy that you talk about in physics one yet. What we're going to do now is do that energy exchange where a big contributor to energy is thermal. So it's related to temperature changes um, and internal energy of gases, mostly gases. Um, and Energy exchange is the first law of thermodynamics. The second law of thermodynamics relates to entropy, which you probably haven't talked about too much. I guess maybe it came up in your intro to chemistry class. Um, but you can think of entropy as kind of thermal disorder. Um, and entropy in the You can make entropy decrease in a small space that you control. Like when you turn on a refrigerator, you're decreasing the entropy inside your refrigerator. But in order to make the entropy decrease inside your refrigerator, you have to make entropy increase outside your refrigerator. And the total entropy in the universe for every thermodynamic process can only increase. I mean, in a perfectly efficient process, it can stay the same. But over time, entropy in the universe uh, continues to increase. Um, I said entropy is a measure of like thermal disorder. Um, you can think of that sort of in the following way. Um, if you're trying to use uh, if you're trying to use thermal energy to do work, to lift objects or to apply forces or whatever, um, in order to extract that thermal energy, you need, as much as possible, you need your energy concentrated in one spot and another spot that has very low energy. Um, so you could have, like, this room could have the exact same amount of thermal energy in it in two different ways. Okay, well, infinitely many ways, but let's think about two. One is the temperature is perfectly even throughout the room, like it basically is now. The other way is there could be sort of an invisible barrier here, and all of the energy, thermal energy in the room is on this side, and this side of the room is at absolute zero. Okay. Um, it would be very easy to produce a heat engine in that case where all the energy is over here and none is over here. It would be impossible to produce a heat engine in that situation where the temperature is the same everywhere. So even though there's the same amount of energy in both cases, um, in one case it's useful, that energy. In another case, there's no way to extract that energy. Okay. Um, you may have heard the term thermal death of the universe that, is a long way off. You don't have to worry about it yet, not this semester. But, eventually, as thermodynamic processes keep happening throughout the universe, entropy keeps going up and up and up until you get to this point where all the energy is perfectly evenly distributed. And at that point, no more useful work can be done at all, even though energy hasn't decreased in the universe. We lose the ability for that thermal energy to be used for anything. So, anyways, entropy is cool. It's complicated. It's sort of like philosophy. We get to this part of the class where it feels like we have a little bit of a philosophical class, and I like that. Um, and that's related to the second law of thermodynamics that says overall, in the whole universe, entropy can only go up. And then we'll talk about, um, so uh, these are all just physics concepts, but what makes this an engineering class is we're going to talk about using these things for engineering applications. So we'll talk about refrigeration and heat pump cycles. How does a refrigerator or an air conditioner work? how does a heat pump work, um, and how does a heat engine work. I guess I didn't put that in here, but heat engines are going to be a big thing. Uh, Heat engines, an example of a heat engine is a power plant. So, and we'll talk about power cycles that they use in power plants in order to generate electricity or work or whatever they want. Okay. So those are the topics in the class. Anybody have any questions right now about any of that? And then um, I want to talk a little bit about the grade format, the grade breakdown. Uh, Pretty much my grades are almost always just 90, 80, 70, 60. Um, if if there's some reason that the grades are, you know, I give a test that was harder than I meant it to be, and everybody's overall percentages are lower, I might curve it down. I wouldn't curve it up. So um, if the whole class is over 90%, the whole class gets A's in the class. Um, but so you can just basically use 90, 80, 70, 60 as we go through the class to sort of see where you're at with your grade. Um, this total percentage for the class is broken down into these categories, and I'll go through and describe each one. Um, so I'm going from least valuable to most valuable. So the first one is this thing I call professionalism, consistency, and appropriateness. That's 5% of your grade. Next is lecture quizzes, 5%. Then daily assignments and weekly assignments are each worth 10% of your grade. And then the big bulk of it is just exam scores, 70%. Okay, so I'm going to go through these categories one by one. Um, so the first category, 5% of your grade, is based on this thing that I call professionalism, consistency, and appropriateness. Um, and this is just really my combined impression of how seriously you're taking the job of learning engineering. Engineering is it's so uh, in math and in physics. Obviously, like engineering is very closely related to math and physics, but in math and physics, um, there's kind of this culture where I mean, you've seen it in movies and whatever. There's like this kind of idea of this irreverent genius or whatever who does whatever he or she wants because uh, this person is so good at what they do that people allow them to do whatever. And there have been all these famous scientists who've been that way, and mathematicians. Richard Feynman was famous for being that way, and Einstein was famous for being that way. And there's sort of a culture in math and physics that people kind of chuckle at that. Like that's you can be that way, okay? Engineering is not like that though. And so I just want to make sort of a distinction here because engineering is so closely related to those things that people sort of that persona kind of appeals to people. But engineering is a professional degree, and your employers and your future professors are going to want you to behave in a professional way. And so I'm going to want to see uh, you take attendance seriously and being on time seriously. If you can't, if you're not going to be somewhere, let me know. You know, um, I want to see you turn your work in on time. Everybody's going to have times where you can't get something in on time, and I'll always accept things late. But if it becomes a regular thing that every single assignment, half of the assignments, something like that, a third of the assignments are coming in late, uh, that's the kind of thing that I'm grading here. Okay. Um, an appropriate level of participation in class. So I'm always happy to answer questions. Uh, I think it's almost always true that if you have a question, other people have that same question. And so you're doing other people a favor by asking questions. But it can kind of cross a line where if um, sometimes there'll be one person in the class who's asking so many questions that it's derailing the whole flow of the class. If you're asking more questions than the entire rest of the class combined, you should consider that maybe that's happening. You know what I mean? Uh, um, reasonable use of exam rescheduling. Yeah, I'd be happy to reschedule an exam if you need it. But if it's every single exam, um, that's kind of a different thing. Uh, if if you need to give me OSD forms, make sure you give them to me ahead of time. Um, legibility of work is part of this. Um, if I can't follow your steps and I can't read your handwriting, um, that's an important thing for engineers. For mathematicians and physicists, they come in with their crazy hair and maybe they're like, you don't have to understand it. You just believe me, trust me, or whatever. And your professors will sort of chuckle at that, like, oh, you know, but that's not the culture of engineering. Okay. Um, what you turn in, uh, your written work, that's a form of communication. And you should think of it kind of the same way you think of turning in papers. Like I need to be able to follow what's going on. um, reasonable lobbying for grades. If you think I misgraded something, if you think like if you have some work on your test that's over here and I graded the stuff down here and didn't take this into account, of course I want to get your grades right. But if every single exam you're coming to me and saying like, oh, could I get 1 point back here? I think, it just gets to be too much. And all of this is part of just giving a professional face, giving your showing yourself in a professional light. Um, following assignment instructions. So like uh, if the assignment says to turn things in into PDF file and instead you turn in 16 JPEGs, okay, that's the kind of thing I'm talking about. Okay. All that said, that's only 5% of your grade. So. But I am trying to just nudge you towards the point where when you finish your college degree, people are happy to have you working with them in a professional environment. Um, the next category is lecture quizzes. Um, and this will be at the end of Monday classes, not every Monday, but often. Um, It'll be just like a 10-minute thing at the end of class uh, where I will ask you I'll ask you short answer questions about things I've said in class. So there's not going to be any calculations in the quizzes. This is just my way of encouraging you not just to be in class when I say this stuff, not just to take notes on what I say, but to go back and read those notes. And not just once, but regularly. Um, I mean, this is an impossible goal, but the goal that I want for this class is like, what do I want? Like, what would a perfect student uh, know at the end of a semester? I would like them to remember every single thing that I said in the class, and I would like them to be able to do every problem that I assigned in the class. You know, and we're working towards that. I try to, on these quizzes, focus on the bigger things. I'm not trying to trip you up on like tiny little minutia, but I'm just trying to encourage you to read and reread your notes. And one thing I'm going to do this semester that I haven't done before is at the end of lectures, I'm going to um, just ask the class, throw out a few questions that are like quiz type questions. So you just get in the habit of hopefully asking yourself questions as you read through these notes. Um, Okay, then 10% of your grade is the daily assignments. Every class, I'm going to give you assignments, and those are going to be problems like mathematical calculations. Um, I'm not going to go through and grade these. I'm just going to check off whether you've turned them in or not. Um, Although I do have cases where people are um, close to a grade boundary, and and I'll go back into the assignments that are submitted to make sure that everything's been done carefully and stuff. So that stuff can make a little bit of a difference if it comes down to deciding between two grades. But mostly I'm just trying to get you to stay on schedule. Like mostly I'm assigning things every day so that you don't put off, you know, working on this stuff for 3 weeks basically. These daily assignments are going to be submitted online to D2L. And I'd like each one submitted as a single file. Um, so PDF is the way to go. It says a JPEG is okay. Um, if you can do it in one JPEG, I suppose that's okay, but really PDF is a better way to do it. 10% of your grade also is these weekly assignments. And the weekly assignments won't be much different than the daily assignments in terms of difficulty or anything. You can think of them as sort of coming from the same distribution of problems, but these are the ones I'm going to actually like go through and grade and score and give you notes on when something goes wrong or whatever. So these will be a little more helpful for your for getting feedback on how I'm going to grade the exams. One thing about the daily assignments I didn't say, I will provide solutions to about half of the daily assignments. So you can check your work after you do it. And it's sort of your responsibility to make sure that you're thinking about these right and doing these right, since I'm not going to go through them. The other half, um, I won't provide solutions, but if you have any questions, I'd be happy to go over them in as much detail as you want in class or in office hours. I'll do some of those problems like at the start of classes. Um, so yeah, these daily assignments, you have full access to solutions for all of those. These weekly assignments are more, you don't have full access, uh, but um, those are sort of more of an assessment thing. And then the exams, there'll be 4 exams. So each one is worth 17.5% of your grade. Um, One thing that is important to notice about the exams, and this is true of the quizzes too, is they're all cumulative. So like exam 2 isn't just going to cover the stuff since exam 1. You have to make sure you're always going back and refreshing your memory on how to do uh, the problems all the way from the start of the class up to when the exam is given. Um, the quizzes I said are just short answer questions. The exams don't have any short answer questions. It's just pure calculations. And these questions are going to be very similar to the assigned problems. So if you understand the thought process for the assigned problems well, you'll do well on the exams. Okay. The dates are all here for the exams. Um, so the first one they're all on Mondays until the final. The first one is September 21st. So I guess that's the first important day, about a month. Um, I will give makeups if you have something else going on, if you talk to me beforehand. Um, if you don't talk to me beforehand, then I'm not going to do a makeup. But there is this uh, this one other thing about the exams. If you score higher on the final than you do on one of those first three exams, your score for the final can replace that lower score from the. So say if exam two you have a bad grade on exam two, but then you do well on the final, when your final score will count as the final, and it'll also replace your exam two. So if we don't talk about it beforehand and you miss exam two, it it'll show up as a zero until you take the final, and then that final score will replace the score for exam two. Okay. So that it's a makeup policy if you miss a test, but it's also just kind of like a mulligan for if you have one test that you studied the wrong things, or you had other stuff going on, you just have a bad test for whatever reason. It doesn't have to affect your grade. Um, okay, AI. I mean, this is now cheating policy is really just about AI now. This is a class where so the things that I'm grading should not use AI at all. Like the weekly assignments, you shouldn't be using AI. I consider that cheating. Uh, the exams, obviously, you shouldn't be. Um, on the daily assigned problems that I haven't given you solutions for, if you want to use AI to, the ones that I said, I'd be happy to talk about those in class or office hours or whatever. If you want to ask AI for solutions on those, um, you can do that. That's fine with me. Um, but basically, anything that I'm going through and grading and assigning points to how you did on individual questions should not have any AI on it. Okay. Um, okay, and then everything below that is stuff that's kind of required by the school. You can feel free to look at that. I think I'm not going to go through all this, but uh, there's some stuff about that's the school statement on AI, um, Normandale Code of Conduct. There's some stuff about the OSD office, and the OSD office is great. So um, they're very helpful people. So feel free to talk to them if you think they could help you. Title IX statement. Yeah. All right. Anybody have any questions about the structure of the class? Well, we have 10 minutes left. I guess let me just start talking a little bit about. So, we're not going to get into really course content yet, but let me talk a little bit about thermodynamics just generally. Um, you're not supposed to look at other people's graded assignments. I don't, that should not be up there. Uh, 2231. And this is a new section. Oh, lame. Oh, let's see. Well, I guess I'll just make a new. section. All right. Um, so okay, thermodynamics. Um, so we can think of this as exchanges between thermal and mechanical energy. And there are three main uses uh, in engineering. These aren't the only ones, but these are the three biggest ones. The first one and the most important is the power cycle. Um, and this is where we use thermal energy to do work. Um, and doing work also can include electrical work. So this can be used to create electrical power, but it's also can be used to power vehicles or whatever. Um, so this power cycle is engines, power plants. In both of these cases, uh, we're using the energy stored thermally to produce work. Um, then second is the heat pump cycle. And third is the refrigeration cycle. And in both of these two, um, it's sort of like the power cycle in reverse. In this case, we use work to transfer thermal energy. So in a refrigeration cycle, like an air conditioner or a refrigerator or freezer or whatever, you have a compressor inside that is compressing a gas, and that compression changes the temperature of the gas, and then you use that change in the temperature of the gas to transfer energy where you want it transferred. Um, so okay, how does this work? All of these three kind of work on the same principle. Um, so first of all, if you heat gas up, in a cylinder. And before I finish this, let's think about um, a piston and a cylinder. Sorry. So let's say here's our um, cylinder, and then we have a piston inside it. And you have a gas here. Okay. So if that gas expands, the piston rises. This is the piston. This whole thing is the cylinder. Okay, so if you heat up the gas in the cylinder, uh, the piston rises. And the effect of that is that work is done on the surroundings. Um, Sort of the converse of this is um, if, on the other hand, you force the piston down, the gas is compressed, and the temperature of the gas then rises. Okay, so the first one of these is how an engine or a power plant works. Um, you raise the temperature of your working fluid, the gas. Uh, the gas wants to expand. That expansion produces work, which you can use to create electricity or whatever you want to use it for, turn wheels. This second one is how a refrigeration cycle or a heat pump cycle actually work. Um, that is, you use the compressor in the case of a refrigerator to compress the gas. When that gas is compressed, its temperature rises, and then you use that rising temperature to accomplish something you want somewhere else in the path of this working fluid. Okay, so let me stop there for today. This is kind of like, think of this as the heart of what we're going to be talking about. We'll just be talking about the details of how this all works. Um, and you're lucky there's no assignment for tonight. But on Wednesday, we'll cover enough stuff that I can assign some problems. Okay.